All right, this is AP Chemistry Notes, page 32 and 33. At the top here, I mentioned a review of entropy. And entropy is just chaos. It's the amount of chaos. So if you think about things just naturally becoming messy, that's an example of higher entropy. And if you put work in to organize things, that's lower entropy. And I make an interesting note here. I heard a show once talking about technology and passwords for your internet accounts and things like that. And they didn't use this word, but they said you want your password to be non-guessable. So what they were saying is that a good password has high entropy. It needs to be random and chaotic. And I mentioned this concept right here. This is what nature wants. When reactions occur, they occur for a reason. They don't just randomly occur. They either lower the enthalpy, or they raise the entropy, or both. If both happen, that's an amazing situation, and nature's getting all of what it wants. When you have to determine whether the entropy change, or delta S of a reaction, is positive or negative, this is a very rough way to do it. You give gases a value of 100, liquids 10, solids 1. So take this reaction that's given here. Ammonium nitrate is a solid right here. Water is a liquid. So water is a 10. Ammonium nitrate's a 1 for a total of 11. Ammonia is a gas, but there's 2 of them. So that's 200. Oxygen's a gas, and there's 2 of them. So that's 200. So that's a total of 400. So the change, final minus initial, would be 400 minus 11, and you get a strong positive result. So this is a positive entropy change. In other words, we are increasing the chaos of this system. And that just makes sense. I don't think you really need these numbers to help you on this one. It's pretty clear. If you have a solid and a liquid becoming gas and gas, that's got to be an increase in chaos. Now, the next section mentions, what if you have molecules in the same state? What's more chaotic? Well, the basic idea is the bigger they are, the more stuff they have, which leads to more chaos. And there's more vibration and rotation and wiggling that's happening, so that causes more chaos. And you can see that in this example that I have here. I have 3 hydrocarbons. They're very similar, but note, as they get more atoms and bonds, etc., the entropy increases. Now, you can solve for entropies for reactions just like we did with delta H. You can use this summation technique, and it's the exact same thing we did before. You need to look at a different page in the book. It's on page 450, and we'll take a look at that in a minute. It's at standard conditions. So 1 molarity, 1 atmosphere, 25 degrees Celsius. But last time with delta H, we must do it with formation reactions so that we know it will work. Here, you don't have to worry about that. In fact, these aren't based on reactions at all. These are based on raw entropy values. So you don't have to worry about that little F for formation. And also, you'll find last time elements were not in the delta H list because forming an element from itself didn't take any change in enthalpy. But an element, of course, does have some amount of entropy. So let's take a look at that chart right now. That's here. Page 450 in our book. And you'll see the elements have a entropy value. If I look a little lower, compounds have an entropy value. Be careful, some compounds are in here more than once. So you'll see that water in the top of the third column is there twice, both as a gas and a liquid. Why they don't put it as a solid, I'm not sure. And if we keep going, there's an interesting one down here. It's H plus in the very bottom left, right here. H plus has been assigned an entropy value of 0. And then everything else just falls into place around that. So that's kind of weird that you'll see some entropy values of negative. Of course, that doesn't mean they have negative chaos. It just is relative to the fact that H plus was assigned a value of 0. Back to the notes. If you do the summation, again, do final minus initial. So if we look at this example with H2, O2, and H2O, I've got my products here. That's the value for H2O times 2 because of the coefficient. And then I've got my reactants here. And I recommend the same thing as before. Be careful with your math. Even though it's easy math, it's really easy to mess up the negatives and so on. Be aware, this chart on page, let me make sure I get it right, 450 is in joules per mole Kelvin. The other chart was in kilojoules, and most charts are in kilojoules. So if you use this chart, be careful because you're 1,000 times smaller than the other charts. And in this case, we see the entropy change was indeed negative 326.4. And that makes sense because we're going from 3 moles of gas here and here to 2 moles of liquid. So of course, that's far less chaos. And so it makes sense that it's a negative value. All right, next, Gibbs free energy, or the Gibbs-Helmholtz equation. This is a huge concept. So not only do I have my little symbol, but it's got a flag. It's creating dust behind it. There's red stuff coming out the exhaust pipe. This is a huge concept. And the reason that I find it such a big deal is this equation and its friends allow us to calculate whether a reaction is doable on paper. This allows us to design a facility to make chemicals based on whatever reaction without actually doing trial and error. So rather than spending billions of dollars to build a facility to decide and find out, oh, it didn't work, you do everything on paper using equations like this one, and you can figure out whether it's going to work, and then you just have to design the best way around that. So delta G, which we mainly are going to use to tell us whether a reaction can occur or not, is equal to delta H minus T delta S. Now, sometimes you'll see this equation with the little circles, the not, and that just means you're at standard conditions. Sometimes you'll see it without the circles, which either means it's just someone being careless, or maybe it's not at standard conditions, and the equation still holds true. So to remind you, a negative value is a yes, means the reaction is feasible and will occur under the current conditions. A positive is a no. A 0 means you're either right on the cusp or you're at equilibrium. And we can do the summation thing again. So that's what I have right here. The same idea. However, you have to go back to formation reactions again. So delta H, you must do it with formation. Delta G, you must do it with formation, but delta S, it's raw values. Now notice it said this is only good at 25 degrees Celsius. If you change the temperature, all the values likely will change, and you must adjust for that and look up new values at the new temperature. I mentioned that these are on page 635, but you're seeing into the mind of a chemistry teacher, and I'm saying do not look there yet. So I'm not going to take us to that page yet. We're going to do a problem where we don't need that page first, and then we'll do a problem where we do use it. And I mentioned here, you can do Hess law with these. So if you know the delta G of a reaction and you flip the reaction, that's fine. Just flip the delta G sign. If you are adding reactions, you can add the delta G's. If you multiply a reaction by 5, multiply delta G by 5, and so on. These next 3 notes have to do with some things that recently came out from the College Board and AP Chemistry. We used to use this term right here. We used to say a reaction with a negative delta G is spontaneous, but it's been discovered that that leads to some confusion. So it's now been rephrased to thermodynamically favored, so that it means the reaction will occur, but it's not indicating how fast or that it doesn't still need a push to help it out. The second note says that many things that are favored, excuse me, may not occur to some huge extent. So like right here, it might reach equilibrium really quickly. So you really don't get a lot of products, or it may go really slow. So be careful. A negative delta G just means it will occur, doesn't mean it's going to be a very beneficial reaction. And the third note, if they do not proceed at a significant rate, they're under what's called kinetic control. And what that means is there's some point in the process of the reaction that is difficult for the molecules and atoms and collisions to finish. And because of that, it doesn't mean it's at equilibrium yet. It's still going forwards. It's just going very slow. And there's a good chance it's because it has a high activation energy. And to remind you what that looks like, if we make a chart of just say energy here, and then reaction process going this way, ignore that dark circle right there. If I put my reactants, let's just say here, and products here, if a reaction is still favorable with a negative delta G, it might have a huge activation energy. And that just means of the particles that are colliding, a majority of them will not be able to collide with that much energy to actually move forward. Very few will actually make it. And that's what they're talking about, a high activation energy. Let's take a look at an example here. Now, I really like this example because it makes you do a summation first with number 1, a summation with number 2, and then you use the delta G equation. And by the way, from here on, I'll probably refer to this as the master equation. I really find this equation has a lot of power, so I like to give it a strong name. Now, I mentioned, do not use page 635 yet. Of course, you could just jump right to number 3 here, and you could look up what the delta G is on page 635, but I don't want to do that. So ignore that and don't go there yet. So using page 207, you can do summation for the delta H of the reaction, and I encourage you to pause the video, try it for yourself, and make sure you get this. That was last lesson. Likewise, on page 450, do the same for the delta S, and you should get this. So again, pause the video and try it out for yourself. Now that we know delta H and delta S and temperature was given here, even if it wasn't given, you could probably assume 25 degrees Celsius. You can plug it into the master equation. So here is my prior value for delta H, my value for delta S. Notice I had to fix my units. If I go back up here, This is in kilojoules. This is in joules. And I chose just to go with kilojoules, and that's usually a good choice. That's why my value became 1,000 times. Not 1,000 times wiggles, 1,000 times smaller. Plug in the temperature in Kelvin because it says Kelvin right here. And you get a positive, meaning this is not spontaneous or not thermodynamically favorable, which means under the current conditions, it will not happen. Based on this concept, the reaction is saying, will calcium sulfate dissolve in water to form calcium sulfate ions at this condition? Based on what we've calculated, it's a no. It will not do it. In other words, it's not, took off there on me, not very soluble. We will cover solubility and things like that more in the future, but this should be familiar from last year. I remember sometimes at this point, students look up the value on page 635 and they say, wait, it's a totally different value. It's because on 635, it's a formation reaction. And what we have here, this is not a formation reaction. So that's why our value and the chart on 635 will not work. Unless you had a chart of reactions of this type, which would just be dissolving things in water, then you can't use that. Okay. Here's one where we just take the direct approach. We're just going to jump right into solving for the delta G using summation. So will HCl gas, known as hydrogen chloride, dissolve in water to form ions, which we know is hydrochloric acid, be spontaneous at 25 degrees Celsius? And in this case, we are going to jump to page 635. So let's take a look at that. If I scroll to it, you'll see it is quite, let's skip that for now, quite a huge chart. So it takes up the entire page of 635 and actually continues on the next page, 636. And these charts show you everything. They show delta H of formation, they show delta G of formation, and they show the entropy values. Notice the elements, like if you look at the very first one with silver, its delta H is 0 because forming silver from silver takes a 0 energy. And the delta G is 0 because there's nothing happening. It already is itself, but there is an entropy value. So back to the problem, which references this table. Again, products minus reactants, or final minus initial if you prefer that. Here are my products. Here are my reactants. Go through the process and you get this, which means yes, it is, again, you're looking at my old notes. I would not use that word anymore. I would say thermodynamically favorable. It's a lot more of a mouthful, but actually is more useful in this case. And then it happens. So what it's saying is if you bubble HCl gas into water, you're going to end up with hydrochloric acid. And that indeed happens. I mentioned the units down here, and I say overall, I don't put the moles in the answer, and that's fine. If you want, you can go with kilojoules, or again, you could do kilojoules per mole reaction, which really is the safe way to do it. So I encourage you to try and use that way of denoting things when it's appropriate. And that should take care of the notes for 32 and 33.